Hello, this is Ertan Taskin from Stochos and Engineering, and in this video I'll be demonstrating an application from objective to the optimized design, web app generation powered by Stochos and GenAI. This work is a continuation of the two previously published blogs and videos, and I will demonstrate those here. You can go ahead and check the Stochos website resources on the blog, and there are two references that you will find. The first one is the probabilistic inference by Bayesian optimization application on the 2D benchmark case, which is the exact same case that I continue to work on with this new video. And the second reference is actually the 3D geometry prediction using the data from this optimization for generating a Stochos app. So let me give you a bit of brief background information. We have this kind of a simple a sort of a showerhead geometry where we have inlet region and outlet region, and outlet inlet conditions specified here, as well as some outflow region specified on the bottom portion of the geometry, and six openings, circular openings, for which the diameters of them are specified as parameters. So I wanted to modify the parameters and get the optimum design to get the highest pressure drop as well as a uniform pressure distribution in the outflow region. So in the first application, we used a probabilistic inference Bayesian optimization in the OptiSlang, and performed the analysis to get the most appropriate designs. In the later application, then we continued to utilize the data generated while preparing this work, and with some additional codes to create an app, a web app, to predict the geometries of the conditions that are already studied in this optimization work. So in this particular work, I will continue with, I will change the topic slightly to create an app already to change the output conditions, such as the objectives, and achieve the optimized design, again utilizing a web app. So this schematic work frame is shown with this figure here. So we have two scripts in this work. We have a train model script, which utilizes the geometries from the previous work, as well as the results files, again from the previous work. And the Stochos train model script utilizes a DIMGP a regression model, a deep infinite mixture of Gaussian processes, and to create a fitted model. Once the fitted model is generated, we use a second script to create an application. The application uses the model as well as the again previously generated results files from the CFD work, of course. And then finally, we obtain the app browser so that we can go through the changes on the objectives and immediately see the results. So I would like to briefly show you the script. Particularly, this is for the train model script. And as I mentioned, this script reads multiple files, and both geometric and the scalar data-wise, and it generates the 3D model with the regression analysis. And if I scroll down, I will show you the corresponding section of the code where the functions are read, as well as this dimgp regression function creates the trained model, and it saves the model with this name, press well model. And in the second phase, we're going to go to the second script called app generation 3D. And as you see, this is a pretty intense code, but it basically again reads this, the CSV files, as well as the previously generated trained model to create an app. Train model script is run under the Spider platform, and when it was run, it took a couple of minutes, maybe 5 to 10 minutes totally to complete, to create the optimized model. And after it is done, what we have to do, we have to actually use a different strategy to run the app generation 3D code. So since this is going to be performed under the Streamlit function, we're going to have to use a separate batch file where this function is specified here, and to run the corresponding code. And once we do that, the web browser opens a new screen and brings us the application. So when first model is read, of course there is no geometry at the beginning. So I try to zoom in slightly. So we have two different sliders here. As I said, we're going to get the optimized design and the corresponding parameter distribution, such as pressure in this case, and move the sliders to get the most meaningful objective for us. For this case, it's actually the higher pressure drop. It can be highest or higher. So as you see, when I put the slider, the function runs, and then it creates the file, which we didn't see yet, because we have to push this update mesh and prediction button. And also for the uniformity wise, we want to have a less pressure differential, and that's why it's actually giving us a better uniformity. So once we select those with the sliders, clicking this button is going to bring the corresponding design with the pressure distribution. Yeah, so that design apparently requires large holes. They are not even, apparently, depending on the site. Keep in your mind that I deliberately made this shape of the exterior shape non-symmetric. So I just wanted to see the impact of that non-symmetry on these internal holes when it gets to the pressure, when it gets to the objectives. So, this is the optimum design to achieve these conditions. So let's assume I want to get totally opposite end and bring the uniformity to all the way to the right side. And click again. And this is the corresponding design. In this case, so the pressure scale is fixed. Pretty much it doesn't change, but you can see the distribution is impacted, as well as the design. So, and it's as fast. So I have performed this live demonstration so that you can actually see how fast we can get the optimized design with the suggested objectives. So this concludes this work as well as the previous works. I hope you enjoyed this. Thank you.